We're learning about the lathe today. It's an extremely interesting machine tool. It has the nickname of being the mother of all machine tools. It's called that because it was really the first machine tool. There's records of lathes existing as far back as 1300 BC. The first metal lathe was invented in the late 1700s, and while many things have obviously changed over the years, the main functionality has stayed the same. So let's start with an overview of that functionality. What we're looking at here is a standard lathe. This is what we would call the headstock, and it contains a spindle and a work holding device. In this case, this is a 3-jaw chuck. What separates the lathe from a mill is it holds the work in the spindle and rotates the work and machines it with a fixed cutting tool. The advantage to this is everything it makes is round. In fact, it's very difficult to make something not round on a lathe, where on a mill, it's very difficult to make round parts. Things that we make in a lathe are shafts. We can make anything with a cylindrical bore, anything like a bearing race or a long shaft, an axle. These are parts that are commonly made in the lathe. So we talked about the headstock. We talked about the 3-jaw chuck. The next thing to notice about a lathe is the ways. The ways extend from the headstock all the way to the tail end of the lathe. These are precision machined surfaces. What they do is they keep the other parts of the lathe, the carriage, the tailstock, aligned with the headstock. It's very important when you're making a part that all these things stay in line. The ways are what do that. It's also very important when operating a lathe to protect these lathes. You don't want to, these ways, you don't want to drop a wrench, tool, or chuck anything on these ways, because any damage to these ruins the precision of the lathe and shorten its life. Moving this way with the lathe, this is what we call the carriage. The carriage moves back and forth along the ways and is what carries all the controls and the tool that we use for machining the part. The carriage, on top of the carriage is mounted the cross slide. The cross slide is what moves the tool back and forth. This is what's going to change the diameter of our turned part. Down here, attached to the cross slide, is what we call the apron. The apron is what carries all the controls. So this has our longitudinal feed. This is what allows us to move the tool back and forth in axis with the part. It carries our feed lever. This is how we engage and disengage the power feeds for the lathe. It carries our half nut lever. This is how we engage and disengage for threading. And it carries our lever for turning the spindle on and off. It goes up to turn the spindle forward, and it goes back to turn the spindle backwards. As we keep moving this way, we have a tailstock. The tailstock is what is used for supporting long cylindrical work. Our tailstock is used, we can swap it out and put a drill chuck in here so we can drill on center of the part. In fact, anytime we need to do operations that are dead center on the part, we're likely going to do it with the tailstock. Something that you'll notice about a lathe are these rods and the screw right here. The bottom rod, as you can tell, our power switch is twisting this rod. This is how we communicate to the headstock to turn the spindle on and off. And the reason it's a rod is so that anywhere we have the carriage, we have our power switch right here. Moving up, we have the feed rod. You'll notice it has a groove that runs the whole length. This is what is communicating the power from the headstock through to our carriage so that we can operate our feeds. When it's running and we have our feeds activated, you will see this rod spinning. Up above here is a precision lead screw. This is how we make threads on the lathe. This lever engages this screw, and drives our carriage back and forth in a very precise manner to make and cut threads. It's important to be aware of these three rods because when operating a lathe, they are all rotating, and you'll notice you're not protected from them. If you have dangling clothing, they can easily get caught in the lead screw or the feed rod. So you always need to be careful to keep hanging clothing away from these screws and rods. Moving down here, we have our foot brake, sometimes called the E-brake. We talked about this in their safety video. This is one of the most important parts on the lathe. If something is going wrong, if something is out of control, if you're about to throw the part or you're taking a cut that you don't feel is in control, your first operation, step on the brake. It cuts power to the spindle, it cuts power to the feed, it has a physical brake that actually stops the chuck. It's going to stop things from getting worse quick. Moving back here, we have a chuck guard. This has a switch on it that does not allow the spindle to spin unless the chuck guard is in place. This is a new requirement. All OSHA shops must have chuck guards on their lathes now. It also keeps the operator from getting chips in their face or oil in their face. Coming back here, we talked about the headstock before. Here's where all our controls are to control our feeds and speeds here. One very important thing to note about all the controls in the headstock, these are not to be operated while the lathe is spinning. We can change anything in our apron while the spindle is spinning. That's fine. But anything in the headstock, we should not be moving these levers while the lathe is spinning because you're going to grind gears and it's going to cause damage. So never use these while the spindle is spinning. Up here, we have a digital readout. Now, we'll talk about hand wheels and hand dials, and this is a very accurate way to make a part. The digital readout tracks your two axes just like the hand wheels, but it's a lot more convenient. You'll notice we have a Z-axis here for longitudinal feed, and we can see it tracks that, and we have X for our cross feed right here. And we can zero those, and it makes making parts to size very easy. Let's take a moment and look at the controls on the headstock. The first thing you're going to do to power up the lathe is twist this button to the right and see that the power comes on. Pressing the button in turns it off. Twisting it to the right and letting it snap out is what turns the lathe on. Next to the power button is a jog button. You use the jog button to move the spindle slowly. You can use this to help shift the lathe or to reposition the chuck. Next to the jog button is your spindle speed control. Now, we're very lucky on our lathes. Our lathes are controlled by what's called a variable frequency drive. It means changing the speed is nothing more than rotating this knob and looking at the speed up on the display. Many older lathes have a series of levers and buttons and switches to shift the gears to control the speed. Once again, on our lathes, all we have to do is twist the button and look at the display to check the speed. To the left of the speed control is a coolant button, a coolant switch. This would be if we had coolant on the lathe to turn the coolant on and off. We do not use coolant on our lathes, so we do not need to use the coolant switch. It will always stay in the off position. Moving all the way up here into the corner, we have our high to low switch. In high range, we can turn from 300 to 2200 RPM. In low range, we turn from 36 to 300 RPM. Down here, we have our feed direction control. When the lever is in this direction, if we engage the feed, the carriage will move towards the headstock. We flip it over to this side when we engage the feed. the carriage will move away from the headstock. What we are looking at here is the most common way of holding work concentric to the spindle of the lathe. It's called a three-jaw chuck. It's often called a self-centering three-jaw chuck because when I tighten the chuck, all three jaws of the chuck tighten at the same time. Therefore, no matter what size piece of work I put in here, it holds it concentric to the spindle of the lathe. You'll remember from our safety video, we never leave the chuck key in the chuck and take our hand off. We take our hand off, the chuck key goes with it. This three-jaw chuck has reversible jaws. If I put a larger part in here, I can take these jaws off, flip them around, hold a larger part. We can also remove this chuck and put other work holding devices on here. We can put a four-jaw chuck on there, which is good for holding non-round parts or when concentricity is very, very important. Or we could remove it and put a faceplate or even a collet on there. It's very important when swapping out chucks to always protect the ways. So it's a good idea to put something to catch the chuck if it were to fall on the ways.
This is a four-jaw chuck. You'll notice that, unlike the three-jaw chuck, each jaw moves independently. This allows us to hold non-round objects, like this block, as well as to purposely hold work off-center, such as if we were turning the loads on a crankshaft. A four-jaw chuck can take a bit longer to get your workpiece set up in than a three-jaw, but for some jobs, it's the only way. Something that is important to pay attention to is that there are two locations that the chuck key will fit near the chuck. The screws on the chuck open and close the chuck jaws. Behind the chuck are cam locks that allow for the removal and installation of chucks. Do not confuse the two or you may end up unintentionally removing the chuck.
This is a quick change tool post. It's a very handy feature on a lathe. It allows us to change tools quickly and easily merely by pulling the lever and swapping out for a different tool. In addition, we can change the angle of the tool post by loosening the nut on top, rotating the tool post, and tightening it. It's very important on a lathe that your tool is always on the center of the part. We have an adjustment here on the quick change tool post. So every tool that you have, you can set a different height. And when you put it in the tool post, it always goes directly back to center on the part. On the lathe, much like the mill, we use handles to control our axes of travel. On the lathe, we often refer to this one as longitudinal travel. It's also the z-axis of travel. This on a lathe is often called the cross travel or cross slide. This would be the x-axis of travel. In addition to these two axes, which are perpendicular to each other, we also have the compound. We can set the compound for any angle between the cross and the longitudinal feed, or the x and the z, merely by adjusting these bolts and pivoting at the angle we want. And then we can use this handle to control our compound travel. Let's talk about these dials for just a moment. One thing that is unique about these lathes is they are inch metric lathes. You'll notice on these dials, there is both a reference mark for millimeters and inches. So if we need to track how far we're moving in inches, we would look at the dial here and realize that each of these on the compound, each of these marks is 1/1000th of an inch, as opposed to in metric, where each of these indicators is 0.02 millimeters. In this way, we can use the same dial to track our dimensions in inch and metric. It's important to realize also that the cross slide is marked differently. On the cross slide, in inches, each mark is 0.02 of an inch. And each mark on the metric scale is 0.04 millimeters. There's a very important reason for this. We'll talk about that in just a moment. Down on our Z travel, or longitudinal travel, each mark is 0.04 of an inch. Now, not all lathes are going to have a dial on their longitudinal travel. In fact, most older lathes do not. So the compound is incremented in 1/1000th of an inch. The cross slide is incremented in 2/1000ths of an inch. Why is that? Do the machine tool makers just pick them at random? No, there's a very important reason why that is the case. And that is because the cross slide is incremented in diameter readings. What happens is, because the part is rotating, the tool is removing material from both sides of the part, or all the way around the circumference of the part. In doing so, if you want the numbers that you read on this dial to measure the diameter reduction of the part, it needs to read differently. In fact, it needs to read twice the actual travel of the tool. Now, that can be a little confusing. Let's take a look at a demonstration to make that make more sense. I'm setting up this dial indicator, which is going to track actual travel of our cross slide. And we will zero our hand wheel right here. So now the cross slide is set at 0, and the dial indicator is set at 0. Watch what happens when I move the cross slide 60 thou. Our dial indicator only moved 30 thou, meaning our tool has only traveled 30/1000ths of an inch, even though the dial on here reads 60 thou. Let's go all the way around 200 thou on the cross slide, and we will notice we are back to 0, so our tool has only moved 1/100,000th of an inch. But it's going to remove that 100,000ths all the way around the part, so it is removed 200,000ths off the diameter of the part. Let's talk about the tailstock for a second. We're looking at the tailstock. The tailstock is used to support long work pieces. What we see here is a live center. It supports long work pieces so we can machine them with rigidity. It has a lever on the back side. This locks the travel of the tailstock in place. It has another lever right here. This lever locks the travel of the ram. It has two ways to measure distance moved. We have a scale here on the barrel of the tailstock, and just like the other axes, we also have a metric and inch scale on the hand wheel itself. It's important that the tailstock is always in line with the center of the spindle. If it gets out of an alignment, there's adjustments on either side to help bring it back into alignment. Set up like this with a live center, it's used for supporting a long workpiece. If we want to change it out to drill or ream, all we do is back the handle all the way up, and it ejects the tool. It's called a self-holding taper. So once again, we back the handle, it ejects the tool. To place the new tool in, we extend the barrel just a bit, we slide it in. This tool has a tang, so it has to be oriented correctly. Once we find the location in which it will slide all the way in, we give it a shove, and the tool is engaged, We can slide the tail stock forward, and now we are set up for drilling or reaming or any other operation that is on the center of the part. One of the big advantages of most lathes are the fact that they have automatic feeds in both Z and X direction, otherwise longitudinal or cross feed. Those feeds are controlled by this handle right here. It's very important when you first start using your feeds to do it away from the part. So if the part is in the chuck, you want to move the carriage far away from the part and practice with the feeds so you don't accidentally engage the wrong feed and damage your part. So with this chuck spinning, here is my feed handle. I'm going to pull it out and up, and I engage the longitudinal or Z feed. I shove it back down and in, and it disengages it. To do the cross feed, I'm going to push it directly down. Once again, out and up does longitudinal feed. Notice it is feeding towards the headstock. Down engages the cross feed. Once again, it is moving towards the center line of your part. So I have just reversed the feed handle on our headstock with the lathe stopped. Now, if I engage the longitudinal feed, it moves away from the headstock. And when I engage the cross feed, it moves away from the center line of my part. These are your feed selection charts. On the bottom, we have for metric threads and metric feeds. And on the top, we have for imperial threads and imperial feeds. If we look at this chart, the top chart is for threads per inch, TPI. You need to choose what thread you're intending to make on the lathe and pick that thread out of this chart. On the bottom, we have feed rates. On a lathe, feed is done in thousandths per revolution. It's how far the carriage is going to travel per revolution of the spindle, and you pick that from this chart down here. Once you have picked either the thread that you would like to make or the feed rate that you would like, you are going to look at this column or this row to find the letters that match up to that column. As an example, if we wanted to have a feed rate of 6 thousandths per rev, we would look across here and see AC, and up here and say PY. Then we need to set these dials and these levers to match what we just discovered from this chart. So here we have AC, so arrow is pointing to the A. C, arrow is pointing to the C. P, we have it right here. And then we need to set this lever to Y, which is all the way over. This is where the jog handle comes in. Sometimes the gears don't mesh easily, so a quick bump of the jog handle spins them just enough to get it into gear. When cutting a thread, we use the lead screw to control the travel of the carriage. We use this lever to engage the half nuts onto the lead screw, and we use this dial to control the timing of that. Okay, so we are done working with our lathe today. Remember, like every machine tool, we want to leave it cleaner than we found it, at least as clean as we found it. First thing we're going to make sure to do is not leave our workpiece in the chuck. So we're going to pull our workpiece. We're also going to pull any tools that we have in the tailstock out and replace it with a live center. We never leave the tailstock barrel empty, because an empty tailstock barrel, that is a taper in there. We could get chips in there, we could get grit in there. We want to protect that taper, so we always leave a center in there. You'll notice we don't have air next to our lathes. The reason for that is there's many precision surfaces in here. We don't want to be pushing chips and grit into those surfaces. What we do is we use a brush, and we're going to sweep all of our chips down into a chip pan below. From there, we can empty the chips out the back using a dustpan. Once we have swept all the chips off the lathe, we take a rag and we wipe all of our surfaces down after the fact, leave them chip and dust free. If we're going to wipe down the ways, which we can, we don't want to leave them dry of whey oil. The ways have covered with a light sheen of oil that protects them, and if we wipe all that oil off, it can allow them to rust. So if you were to wipe down the ways with a rag, make sure to run the carriage back and forth so as to re-lubricate the ways before you're done for the day. Thank you for watching our video introduction to the manual lathe. I know we covered a lot today, and it can be confusing if you've never run or at least stood in front of a manual lathe before. What we're hoping with these videos is that when you do actually get to run a lathe, the fundamental skills you've learned will have you making good parts in no time. So that's it. Thanks again for watching. Have fun and stay safe.